We will now see what happens when an inductive load is supplied by a generation source at a distance. There is a factor called power factor which plays a vital role in understanding this subject. Let us see an analogy. Assume that a car is being towed by a heavy vehicle with a rope. The rope used to tow the car forms an angle theta to the direction of movement. The tensile stress R in the rope can be divided into two forces. Assume that P is the force acting in the direction of movement, and Q is the force at right angles to the direction of movement. You know that P is equal to R cosine theta, and it is the cause for the useful work done. The force Q is equal to R sine theta. And this force Q develops only a lateral pressure that contributes nothing to the actual movement of the car. R cosine theta, that is, P is the actual working force. Let us call this cosine theta as power factor. R sine theta, that is, Q is the reactive force which is used to lift front side of the car vertically. This is actually a loss of energy. Let us see another example. Cycle pedaling. When the leg is pressing one pedal downwards to rotate the wheel, the other pedal has to be brought upwards to continue the pedaling on and on. The upcoming pedal does not do any work while it is coming up. But without bringing it up, we can't continue the pedaling. We can now understand the role of power factor in electrical engineering. Assume that power is flowing from generation point G to load point L as shown. Referring to the waveforms, the directions of the voltage and current vectors coincide between B and C and also between D and E. During this time, active energy is fed into the load to do the work needed. The yellow-colored area of the power curve between B and C, and also between D and E, represents the active power. It is in the positive direction. To develop rotating torque in an induction motor, developing a magnetic flux is the first requirement. The energy needed to develop this flux is also sent from G to L in between B and C of the waveform. This flux does not do any work by itself, but it helps to develop the torque. At the end of each half cycle of voltage, the flux goes to zero and a new flux is developed in the next half cycle. The current needed to create this flux travels from the generation point G to the load point L. And when the flux goes to zero, a current is fed back to G from L. The power due to this current is reactive power. This process is a kind of magnetic reversal of energy. The pink-colored area of the power curve represents this reactive power. Between C and D, the voltage is in the negative direction and current is in the positive direction. The opposite polarities of voltage and current result in a negative power of energy. This means that the reactive energy between C and D is now pushed back into the generation source. Thus, we can see that the reactive energy flows to and fro between the generation point and the load without actually doing any work. The current component of this reactive energy also flows to and fro in every cycle between the generation source and the load without actually doing any work. But there will be line losses due to this to and fro flow of reactive current. There will also be voltage drop between the generation source and the load due to this current. We have now understood that these flow of reactive power, line losses, voltage drop, etc. depend upon the power factor. The cosine factor of the angle theta, that is cosine theta, is called power factor. It could be seen that when the power factor is too low, the ill effects on the system are more. These need to be addressed by power transmission engineers. Let us see it in the next lesson.